Hey everyone, welcome back to Everything is Relative with me, Mr. K. And today we're going to be looking at a crash course on the topic of work, energy, and power for Cambridge AS Physics subject code 9702. So this counts as a topic in the first year of your two-year program for A-level physics. And it's a very fundamental and important topic as it talks about energy, which is very important to physics in any form, whether it's at A-level or at university or postgraduate studies. Energy is the thing that we are always very interested in. And so it's important that we understand the fundamentals of energy and what energy means and how we can differentiate energy from power and so on. And so where do we start when we talk about work, energy, and power? So for many of you, you will have some kind of background when it comes to this topic, but it might still be a little bit fuzzy. So let's start with the concept of work, firstly. Now, we give the symbol for work to be W, uppercase W, and in this case, uppercase W, and we say that work done is equal to the force that you apply to an object multiplied by the distance that the object moves, so F times X, in the direction of the force. Meaning if I push a box to the right and the box moves to the right, then the work done is the force that I applied in newtons times the distance that the box has moved. And theta here, so cosine theta that I've added an extra term, is the angle between, remember, the force and the displacement, where X is the displacement actually. The force between F and X is theta. So these are two vectors. Vectors are lines. We can represent vectors by lines. And any two lines can have an angle between them. And so if I have some point mass, let's assume a point mass. It makes it easier to understand. This point mass could be a ball. It could be a block. We're just assuming the center of mass is some point. I push on this ball or on this block with the force F, and the object moves to another point, and its displacement also to the right is X meters. So the work done on this object W will be the force that I apply. Let's assume that's also a constant force to make our life a little easier. We'll always assume constant forces here. F times X times the cosine of theta, where in this case theta is actually 0 degrees because the angle between the force and the displacement, both horizontal and to the right, will be 0 degrees. And so it's simply F times X. And we sometimes wrongly think of work as force times distance. Well, it's not. It's force multiplied by distance in the angle of the force, in the direction of the force rather. And there's a different way we describe work when we use vectors, which we aren't going to do here in A-level physics. But let's assume that I'm now pushing this box. It's quite a small box, and so I have to push to the right, but I also have to push slightly downward. So all of my energy is not going to push the box along the floor. There's a component of my force that's actually pointing downward. It's not the most efficient way, but it's probably an easier way considering maybe whatever's happening. And so again, I have the displacement to the right. The object moves some distance X to the right. And the angle between the force that I applied, I'll call it F again, and the object is theta. Now the work done in this case is the force multiplied by the distance in the direction of the force times the cosine of theta. Now sometimes this method can be a bit confusing. Why do I have a cosine theta just roaming around there? Well, if I think about the force that I'm actually applying, this force is down and to the right. Actually, I can exaggerate this a bit more. This force is down and to the right, meaning there's a downward component of the force and there's a rightward component of the force. Remember, any force, any vector rather, can be broken up into components that are perpendicular to each other. So this force that's down and to the right has a downward component and a rightward component. Now I'll call the downward component Fy, and I'll call the rightward component Fx. And since these are just lines as vectors. I can translate them in space. I can move them around in space. And so this vector Fy, the vertical component of the force, I can shift it to the left. Now Fy and Fx are 90 degrees. They're separated by an angle of 90 degrees, or they are perpendicular to one another. And the angle theta is the angle between Fx, the horizontal, and the force F. And so from here, with a little bit of trigonometry, we can see that sine theta is equal to Fy over F, and cosine theta, SOHCAHTOA, cosine theta is Fx over F, which you can then see means that the component that I'm really cared about, Fx, which is the thing doing the pushing, the horizontal component, if I rearrange the expression above, it's F cosine theta. So essentially, that's where the cosine theta comes from. So the cosine theta should be attached to the F, because it makes a bit more sense. It's the horizontal component of that force. But it doesn't really matter. It's still the same equation for the work done. And so the work done is the force times the displacement, as long as the force and the displacement are in the same direction. So you look for the component of the force that is in the direction of the displacement of the object. And so that's the definition of work done. Work is basically what happens when an object is moved by a force. And the work done is by the force if the force is in the direction of motion of the object, and we say it's on the force if the motion of the object or the displacement is opposite to the direction of the force. So that's, again, just semantics, just a convention that we use. Now, work done is, as you may already know, if you don't, work done has the units of measurement. I'll use square brackets for units of measurement. So the units of work done is the units of force multiplied by distance, since cosine theta is dimensionless. And this is a Newton meter. But since we are too lazy to keep writing Newton meters, we give it a derived unit which we call the joule. And this is uppercase J. So the unit of measurement for work done is the unit of measurement for energy, which we'll see just now, but this is the joule. So I should just write it down. Remember, when writing the unit down in words, even though it's named after a person, it becomes a common noun, so it's lowercase j, J-O-U-L-E, the joule. And so that's work. And we usually start with work because it sort of builds on to our definition of energy a little bit. And so we need work to explain what energy is. Well, not necessarily, but energy is a confusing one. We usually talk about the energy crisis in the world, or how we're going to keep our energy production green. But words like energy, power, strength, force, all of these things have similar meanings in English, but different meanings, very different meanings in physics. So I forgot to mention that the work done here is a scalar quantity. Remember, a scalar quantity is one that has no direction. So even though force and displacement both have direction, the work done is scalar, so it doesn't have a direction. Okay, so it's something called a dot product, which you don't need to worry about unless you've studied vectors. But work is a scalar, doesn't have a direction. And energy, in a very, very simple, loose way, is the ability to do work. So if I were to define energy, I'm going to say energy is the ability to do work. And what did I say work was? Work was force times distance. So energy is the ability to move an object a certain distance by applying a force on it over that distance. So that's basically what energy means. And we can also talk about a very important thing that happens when we discuss energy, in that it's conserved, in that all of our known interactions where energy is involved, energy will be conserved. And so we call this, I should name it first, we call this the law of conservation of energy, the principle of conservation of energy. And this will be a savior for you in many of your AS and A-level topics going forward. Whenever you're in doubt, energy conservation principles usually help you solve very complex problems. So the law of conservation of energy says that energy cannot be created or destroyed. Again, this is something you most likely would have heard of before, but if you haven't, energy cannot be created or destroyed, but it can only be converted from one form to another. And believe it or not, most of our problems, well, at least in the physics space or even in the engineering space, require this one simple law to help us solve for very complicated things. We can't create energy, nor can we destroy energy completely, but we can transfer it from one form to another. We can convert it from one form to another, even if one of the forms of energy is not very useful to us. So energy can't come from nowhere or disappear into nothing, but can move from form to form. And we'll talk about some of the forms a bit later on. But what is important is to maybe just understand some of the orders of magnitude. And the unit of energy for the unit of measurement for energy, rather, is the joule as well. So how many joules is a lot of joules? Well, let's just discuss some basic orders of magnitude. It's good to have an idea when working with any unit of measurement to understand what are you measuring and what are the usual orders of magnitude when measuring that thing. 10 to the minus 18 joules. Well, actually, let me just write everything down and then we come back. What about 10 to the minus 2 joules? What about 10 to the power 3 joules? So if this is the first time you're studying the topic of energy, you probably wouldn't know what energies fit in these categories, in these orders of magnitude. What about 10 to the power 12 joules? And then 10 to the 25. I've just chosen 5 random things in the universe, or 5 actually, and then I'm going to talk about what has those orders of magnitude. So 10 to the minus 18 joules is a tiny amount of energy. And this is actually the ground state ionization energy of hydrogen. We usually don't measure it in joules, but if you convert it to joules, it's quite shocking. It's a tiny number. The ground state ionization energy of hydrogen in joules is 10 to the minus 18 joules. That's something very difficult to measure, if at all possible, directly. What about 10 to the minus 2 joules? So this is a lot bigger than the ground state energy of hydrogen, but still small amount of energy. This is the energy used by a typical LED for 1 second. It doesn't make sense to talk about the energy used by something that can be used constantly, like an LED, so we specifically would say for 1 second. So it's a very small amount of energy used by LEDs. This is why LEDs are very efficient. What about 1,000 joules, 10 to the power 3 joules? So this is the energy that is received from the sun at the Earth's surface. So we have to be very careful how we say this. From the sun at the surface of the Earth per square meter per second. So energy received from the sun at the Earth's surface per square meter, I'll say every second. It's a little bit easier to sort of conceptualize. So we receive 1,000 joules of energy from the sun on every square meter patch of the Earth's surface every second. So you cannot have more energy irrespective of how many solar panels you have per square meter every second. That's the maximum amount of energy. If you have a square meter solar panel, you're not going to get more than 1,000 and a bit. I think it's 1.4 thousand joules per square meter for every second. What about 10 to the power 12? It's a huge amount of energy. So this is the amount of energy roughly from the explosion that happens when 1 kiloton, 1,000 tons of TNT is used. So energy from explosion of 1 kiloton of TNT. So that's quite a significant amount of energy. And I've also omitted smaller energies than 10 to the minus 18 and also larger energies than 10 to the 25. But there's energies that are much higher. But 10 to the 25 is the total energy received on Earth from the sun in 1 year. So now we're considering the entire Earth and all of the radiation energy that we receive from the sun in 1 year on the Earth's surface would be 10 to the power 25 joules, which is a lot of energy. If we could harness all of it, we would not have any energy issues. And so there are energies higher than this, energies of quasars, energies of galaxies, rotational energies of galaxies, smaller energies than the ground state energy of hydrogen, like the energy of a photon of a very low frequency. But here's just an idea of the orders of magnitude of some of the energies that you might come across in your journey in physics. So what happens when work is done? Well, when work is done, energy is transferred. Energy goes from one form to another. And that's basically what work does. So if I think of, let's just think of a mass. I'm going to take some massive object. We're going to discuss this type of energy a little later on. But this mass at some height above the Earth's surface, we say has gravitational potential energy. So if there's any object at a height h, I'm going to call it capital H, above the Earth's surface, then this object has gravitational potential energy. We'll discuss the formula for that a little later on. But let's say I now take this object, the same mass, and I move it closer to the Earth. It starts to fall, let's say. It starts to move closer to the Earth. And it's now a distance h to the surface of the Earth. So that if I compare, the distance little h is smaller than the distance big H. So it's now falling towards the Earth because of gravity, and it has a speed v, and it's now a distance little h to the Earth. So now it has two types of energy. It has gravitational potential energy. I can simply say GPE. That's good enough. I can say gravitational potential energy, but it's also moving. So again, we'll discuss this a little later on, but there's another type of energy that it has because of its motion, which we call kinetic energy. And so actually I have its initial gravitational potential energy now becoming gravitational potential at its new height, which will be slightly lower, because there's a kinetic energy term that's being added here. The total energy will remain the same. And so therefore, what I can say is that the initial gravitational potential energy, now again, I'm assuming there's no air resistance, I'm assuming no heat loss, I'm assuming very ideal scenarios. The initial gravitational potential energy is equal to the sum of the final gravitational potential energy plus whatever kinetic energy is gained, Ke. This is the principle of conservation of energy in mathematical form. So this is the conservation of energy like we stated before, but in mathematical form. It initially had gravitational potential energy. The energy can't completely disappear into nothing. So it becomes its final gravitational potential energy, which is now less, plus some kinetic energy, which it has because it's moving. Kinetic means to move. So this equation is the mathematical form of the conservation of energy, which you're going to use very often, in fact. And the other thing we can talk about is the efficiency of doing work. And so efficiency, we don't really have a symbol. Well, at this level, we don't have a symbol for efficiency. But efficiency is basically how efficient are you? How much useful work are you doing now that you're very short time away from your exams? The efficiency of anything that we require to give us some output energy is the amount of energy we get out divided by the amount of energy we put in. So very few things that provide us with a source of electrical power, very few energy sources are anywhere close to 35 to 40 to 50% efficient. Most of our electricity generating methods are a lot less than 30%, 40% efficient. And so we're not getting all of the energy out that we put in, and or not all of the energy out that we possibly could. And so we don't use all of our resources to completion. But the efficiency can never be more than 100%. So unfortunately, if you were trying to build a perpetual motion machine or limitless source of energy, you can stop now. This is not going to get you anywhere. You can't have more energy out than you put in. That's because you would be creating energy from nothing, which we said is already impossible. So let's imagine that I had a ball. Believe it or not, this is a round ball. It's the top of a hill. And because it's the top of a hill, it's some height above the Earth's surface. It has some height above the center of the Earth, or the lowest point of the Earth, sea level. It has some gravitational potential energy. It then encounters a slope and then will level off at sea level, where it will end its journey. And at the bottom, it has no more gravitational potential energy, but just kinetic energy, just because it's moving. If it's going to move down the slope, and let's assume that the slope is a bit rough, so there's going to be something that you've learned before. There's going to be a resistive force acting on the ball, and that resistive force is going to be friction. Now, friction is going to cause the ball to heat up as it rolls down the bank, and this heat energy we call thermal energy. Another word for heat energy is thermal energy. We can use these two words interchangeably for now. And this thermal energy is going to be quote unquote lost as the ball rolls down the embankment and makes it to the bottom. And that's because of the friction. So there is work being done by the friction on the ball. And so some of the energy goes to heating the ball up. Not all of the initial gravitational potential energy becomes the final kinetic energy. So the efficiency here is the output, the kinetic energy at the bottom, divided by the gravitational potential energy at the top. And this is going to be less than 100%. So in reality, we cannot avoid energy losses. You should always account for energy losses whenever you are setting up an experiment or trying to measure the relationship between things, where it's very possible that energy can be lost in the process. And so the kinetic energy is less than the gravitational potential energy. And the gravitational potential energy initially is equal to the kinetic energy plus another form of energy, which is heat that is lost as the ball rolls down the bank. The more friction there is, the more heat loss, the lower the final kinetic energy, which kind of makes sense. The ball will roll faster if there's less friction. If this was an icy surface, it would roll very fast. If it was a very rough, rocky terrain, it would move quite slow because of the amount of heat loss because of friction. And so that's the idea of efficiency. Now, efficiency will tell us how much of useful energy is coming out divided by how much useful energy goes in, and basically tell us how efficient our energy creating device is. Now, efficiency can also be used to describe, or can be used when we discuss things like power. But how do we think about power? Well, again, we throw this word around quite loosely when we talk about energy generation for electricity. But basically, in science, power is the rate at which we do work. The rate at which work is done. Please note I'm saying that it's the rate at which work is done. Do not say rate at which work is done per unit time. The word rate already infers that we are saying per unit time. So the word rate includes per unit time in it. And So if I write this as a equation, power is work done and divided by the time it takes to do that work. So let's calculate the total work that I'm doing divided by the time it takes for me to do it. And mathematically, this will be P, we give it the symbol uppercase P, is W divided by T, which means the units of measurement for power is a joule per second. How many joules am I exerting every second? And we give it the symbol uppercase W. Don't confuse uppercase W, the symbol for the unit of measurement, as compared to the symbol for work done. And this is the watt, again, small let W-A-T-T. So the unit of measurement for power is the watt. For example, 100 watts mean I'm doing 100 joules of work every second. And so if my power supply for my laptop is 45 watts, that means my laptop can convert 45 joules of electrical energy to chemical energy to charge my battery every second, or whatever. And so that is what power is. But a quick note on power is that not every time you tire yourself out doing something are you necessarily exerting any power. So remember, power is also a scalar. It's a scalar divided by a scalar, so that's happily a scalar. So this is you pushing a very large rock. Surprisingly, this rock is circular, but doesn't matter. You attempting to move this rock and you fail because the rock is the same size as you are and probably much heavier. There's no motion of the rock, so there's no work being done. So there must be no power, because power is the rate at which work is done, but since no work is done, there's no power. But you're sweating and huffing and puffing, and you want to get paid for a hard day's work, but you haven't actually moved anything and you haven't physically done any work. So what you are doing is converting chemical energy in the food that you've eaten over the course of the day to thermal energy as your body heats up, as you begin to sweat and perspire, but you aren't actually doing any work on the rock. So yes, there can be energy changes, but for the mechanical energy of the rock at least, there's no change. It's not changing and gaining some kinetic energy or gaining gravitational potential energy, so no work is done. So remember, if you're not moving an object, there will not be any work done. Another way to think of work is, let's say I actually can move the rock at some constant speed v. Then the work done, we said, is force times distance, and let's assume the rock is moving in the distance that I'm pushing it. What W is F times x. But if I divide both sides by time, what I get is W over T is equal to F times x over T. Now I wrote this in this way for a very specific reason. Work done per unit time is power, and we'll assume the force is constant that I'm applying on the rock, and x over t, displacement over time, is velocity. So we sometimes call this motive power, but if I apply a force on an object and I move it at constant velocity, then the power that I am exerting is force times velocity. Now remember, obviously, if I'm applying a force to an object and it's moving at constant velocity, then I'm moving it against some resistive force. So usually this will require some resistive force so that even though you're applying a force, it moves at constant velocity. And so the power that you're exerting is force times velocity. So we've talked about work, we've talked about power, and we've briefly discussed some of the types of energy. And now we'll talk about these types of energy in a little more detail. The first one being elastic potential energy. But I think it's important that we first discuss what exactly potential energy is. And again, I'll type this out. Now, in general, potential energy is the ability of an object to do work. That's what energy is. The potential energy is the energy. What type of energy? Due to its position or even shape. Mostly we say potential energy is due to the position of an object, which kind of works its way into saying shape, but we can say shape as well. So potential energy is the energy of an object has due to its position, due to its shape. Like gravitational potential energy is the energy that an object has due to its position in the Earth's gravitational field. But why do I say shape? Well, specifically because of the heading that I wrote, elastic potential energy. And if you haven't studied this yet, it'll be the next topic. But what happens if I deform a solid? Well, if I deform a solid, and I deform a solid elastically, meaning it's going to want to go back to its original state, then by deforming that solid, it stores what we call elastic potential energy. An example of this would be a rubber band or a spring. So a rubber band can be stretched and can be used to fly off and sting someone, or a spring can be used to make a mass move, or to push an object or pull an object, or even raise or lower an object. And so that energy is elastic potential energy. So let's imagine I have some horizontal ceiling, and from that ceiling I hang a spring. If I simply hang the spring as is, the spring will be what we call unstretched, meaning it's not being stretched or compressed. So this is an unstretched spring, and we say that the spring has zero elastic potential energy. So it doesn't have the ability to push or pull or raise or lower anything. But if I wanted to make the spring be able to do work on something, I can stretch the spring or compress the spring. So let's take the same spring and let's attach it to some mass, m, some block, maybe a wooden block or a metal block. And you know from experience that the spring is going to stretch a bit. And so now the stretch spring does have an elastic potential energy. If I remove the mass, the spring will shoot back to its original shape and size. And so it has a non-zero elastic potential energy. Or I could say just has some elastic potential energy. And so we'll discuss the actual equations behind elastic potential energy in the crash course for deformation of solids, but that's just an introduction. So elastic potential energy is when I deform a solid elastically, and I can then use that energy later on to do some work, which is basically what potential energy is in general. But let's come to something that is a little bit more relevant to this topic, and that's gravitational potential energy. Now we're going to teach this to you now, and you're going to learn it again in year 2 of A-level physics, and you're going to learn it a lot more advanced there than you do here. So we're going to take some liberties when we describe what gravitational potential energy is now, and we'll come back to later on to discuss what it actually is. But basically, gravitational potential energy, if you would jump and while you are in the air for that short moment of time, you have gravitational potential energy, and then you will move back down, gaining kinetic energy. So it's the energy possessed by a mass, specifically by a mass, because you need to have mass to have gravitational potential energy, due to its position or relative position in a gravitational field. For now, we're only going to talk about the Earth's gravitational field. So gravitational potential energy, the energy that an object has because it's somewhere in the Earth's gravitational field, because it's above the surface of the Earth. So let's imagine I had a mass, again I'm just using wooden blocks or metal blocks, which is blocks in general, with some mass m. There's a force on the block, which is its weight acting vertically downward, mg. And this block is chilling somewhere above the ground at a height h. So momentarily this block is at rest. There are no other forces acting on it beside its weight, And so the work done to maybe raise this block to this height is the force multiplied by the distance. And the force that I would need to raise this block to the height h would be the same force as its mass, as its weight rather, mg. And the distance that I moved it is the distance h. So the work done to move the block to a distance h is mgh. And the work done is the amount of potential energy that it gains. So it gains a potential energy of mgh. And g here is the free fall acceleration, or the acceleration due to free fall on the Earth's surface, or near the Earth's surface, 9.81 meters per square second. So potential energy is mgh if you know the mass of the object and you know its height from the Earth's surface, or its altitude, or how high it is, or how distant it is from the surface of the Earth. That gives you the gravitational potential energy. Now, what about an object that was initially, so it has mass m, and it was initially, let's draw the surface of the Earth. So let's say it was initially very low down and we moved it upwards, we carried it upwards or whatever. And so it initially had a height of h1 above the surface of the Earth, and finally it had a height of h2 above the surface of the Earth. Then the change in gravitational potential energy is mgh2 minus mgh1. Delta EP is mgh2 into minus mgh1, which is simply mg delta h. So the change in gravitational potential energy is the increase in gravitational potential energy as the object increases in height. If the object falls and gets closer to the Earth's surface, it is losing gravitational potential energy. So gravitational potential energy is the energy that a mass has due to its position in the gravitational field. The greater the value of h, the greater the gravitational potential energy. As the object moves towards the Earth, that gravitational potential energy is lost, but is converted to kinetic energy, which is why if you fall from a greater height, you have a greater final velocity, because you have more initial gravitational potential energy to convert to kinetic. Talking about this thing of kinetic energy, what is kinetic energy? Now, simply put, we're only going to discuss one type of kinetic energy. There are a few, but we just described the most basic one for now. And in the most simplest terms, kinetic energy is the energy that something has because of its moving. So kinetic energy is the energy of an object due to its motion. So if anything is moving, it has kinetic energy. How it's moving will tell us what type of kinetic energy it is, but we're only going to discuss one type of kinetic energy for now. So any object in motion has kinetic energy. This is why I say when the block falls, it loses gravitational potential energy and gains kinetic energy. Remember, energy must be transformed. So again, I'm going to use the example of a block. Most basic example I can think of. It has a mass m. I am very strong, so I push this block from the left, it moves to the right, and it starts with a speed u. As I push the block, again, I'm going to assume there's no frictional forces happening, but obviously it accelerates as I push the block because I'm applying constant force without any resistive forces. And the block moves let's say it moves some distance s. I'm going to use s as a displacement here, but you'll see why, because it takes us back to our equations of motion. Now, the force that I apply from Newton's second law is the mass of the block multiplied by its acceleration. We'll assume again there's no resistive forces, no friction, etc. But we also know that the final speed v squared is equal to the initial speed squared, u squared, plus 2 times the acceleration times s. So v squared is u squared plus 2as, meaning I can write the acceleration as v squared minus u squared over 2s. I think you can see where this is going now. So now that I have an expression for the acceleration, I'm going to put it into the equation for the force, and what I get is that the force, or rather 2 times the force times the displacement, is m into v squared minus u squared. A little bit of algebra to do in between, but I'm sure you can handle it. And so force times displacement is a half mv squared minus a half mu squared. But wait a minute. Force is in the direction of the motion, so force times displacement is work. So the work done is a half mv squared minus a half mu squared. But the work being done is the change in kinetic energy. The kinetic energy increases as I apply a force onto the mass. So this work done is the change in kinetic energy. A half times the mass times the final speed squared minus a half times the mass times the initial speed squared, which then tells me that if I were just moving some object we're just moving with a constant speed v, then it would have an associated kinetic energy that's a half mv squared. And we call this, the only part of kinetic energy that we're going to learn, this is called translational kinetic energy. To translate an object means to move it back and forth, left and right in a straight line. We also get rotational kinetic energy, which we're not going to study just yet, but that's for an object that is in rotation. But this is basically, we just call it kinetic energy, by the way, but it's actually translational kinetic energy. So at a constant speed v, the kinetic energy of an object is half multiplied by the mass times the speed squared. So as the speed increases, the kinetic energy increases exponentially. You double the speed, you quadruple the kinetic energy, and so on. And this is why very heavy objects, objects moving at a very high speed that don't have a very great mass can still have lots of energy, like a bullet, for example. Weighs a very small amount, but it travels very fast. So v squared means it still has a very high kinetic energy. So this was a crash course on the topics of work, energy, and power. Not too difficult, but very important, very fundamental to everything you'll ever do in your journey in physics. So it's very important to understand the basics and to read and make sure you understand how energy changes form, the law of conservation of energy, the different types of energy, the orders of magnitude, and so on, so that you become more familiar when answering more complicated questions, how to think about energy and how to conceptualize it. So I hope this video was useful. If it was, please leave a like and a comment, subscribe to the channel if you haven't already. And that's all from me, Mr. K, for now. I'll see you again next time on Everything is Relative.